My name is Bob Zook. I'm the chief engineer on the SCINI project, and we're here in Antarctica right now. We've developed an ROV that fits through an 8-inch hole drilled in the ice, and it's a torpedo shape. It goes down through the ice, and basically we're able to swim around and explore the seafloor with it. Primarily, SCINI's job is to collect imagery. There's a forward-looking camera for the pilot, and there's a downward-looking camera for the scientists. With all of this hardware inside the camera portion of SCINI, we generate a lot of heat. And that heat has caused us some problems. The camera bottle itself is made out of aluminum and is actually very good at conducting heat, but the electronics inside have trouble getting the heat to the aluminum so that it can be conducted out. One way of resolving it was we could run it for a while, turn it off, and let it cool down. And believe me, we did that for short periods of time. But we came up with a better solution.
You can figure out how to cool something. What you need to ask yourself is, how do you get heat away from an object? Okay? When you cool something down, you're not adding coolness to it, you're removing heat from that object. And so knowing how heat goes from point A to point B is going to be your first order of business. Heat is transferred in 3 ways. First, that's what's called conduction. Now, conduction, you probably became familiar with at a very young age. Probably the first time you went up to your mom or your grandmother, they're cooking, and you tugged on their apron and you grabbed the frying pan and you started crying. It was the first time in your life that you were aware of the process called conduction. Conduction moves heat through a material, through the frying pan. When the frying pan is sitting on the stove, this is getting hot. It's got a metal handle connected with metal fasteners. That heat gets transferred through this pot to that handle. Okay? As the heat spreads out, it's being spread out by the process of conduction. All right? It is conducted through the pan. So conduction is probably the first way you realize as a child how heat is transferred. And it's heat transferred through a material. The second way heat is transferred is through a process we call convection. Now, convection, you may not have ever seen. Or if you have seen it, you may not have realized what you were looking at. Convection is a process by which heat is transferred not through a material, not like the frying pan, but by the movement of the material itself. Convection is caused by differences in density of the material. As you may know, density is a ratio of one's mass to one's volume. It's why a battleship can float, but a penny will sink. It doesn't have to do with the total weight of the object. It has to do with this total density and how it relates to the object it's trying to float in. Air can change densities, primarily by heating up. When something heats up, when air heats up, it expands. Once it expands, it becomes less dense. Because why? Its volume gets bigger. When it expands out, this V gets real big and makes its overall density drop. Once that density drops, it'll essentially float up, just like a battleship floats, up in the air. Notice when I strike these matches is a column of air that's already extending above them, that's rising up, that's heating, expanding this volume, causing this density to decrease so the column of air can rise up. That's the process that you're not seeing yet. But as soon as we blow out the matches, you can start to see it. You can start to see that column of smoke rise up in the air. You don't see air when you see smoke. You see smoke and ash when you see smoke being carried up by the air, whose volume was increased by the heat of the match, which lowered its density, which made that bundle of air float up, essentially, since it is less dense than the surrounding air. The third way that heat is transmitted is a little more elusive to us even than the convection. We can still occasionally see the convection, and we know what happens as it happens through matter. But radiation doesn't even have to have matter to flow through. A perfect example is the sun, which bombards us with solar radiation 24 hours a day. There's no matter in outer space, right? That's why I call it space. There's no matter there. You've got nothing from the sun other than a couple planets till you get to the Earth. The radiation that hits the Earth from the sun is invisible. We can't see the bulk of it. A few of the wavelengths we can in the visible spectrum. But for the most part, radiation is an invisible thing. We don't realize that there are so many other frequencies being radiated to us by the sun that we don't pick up on. Our skin can tell us that there's some heat there by infrared radiation. Our eyes can tell us that there's some visible light there in the visible spectrum of radiation. But other than that, there's not much other sensing we can do as humans that we even know radiation exists. It's the most elusive of these three types of heat transfer. And it's the one that's going to be the least applicable to the SCINI's camera bottle overheating. Okay? We can't control the amount of radiation that that camera or the batteries or any other thing in that camera bottle gives off. That's something inherent to the material. But what we can control is either how much heat gets conducted or convected out of that bottle. So those are the two methods of heat transfer we're going to focus on in relation to SCINI. Now remember, the camera bottle on SCINI has to be easily taken apart. In case you ever need to change out a camera or fix anything, they don't need a lot of extra bracing in the camera bottle that they have to deal with when removing components. Okay? That kind of eliminates any type of conductive process to get more heat out of there. You don't want to build any more braces going from the camera to the outside of the camera bottle to transfer that heat, much like it would be through the handle of this pot. So, although we have no control over the radiation, like we had mentioned, we don't want to really do too much with conduction either, because it's going to add weight and complications whenever we have to disassemble it. Convection is the best choice for SCINI's camera bottle overheating problem. Remember with convection, remember the match, how the flame caused the air to absorb that energy, expand, okay, which caused its volume to get a lot bigger, remember? Once that volume got big, its density went down and it floated up. That's the basic idea, all right? So how do we control these air currents inside this camera bottle? What can we do on our end to make these currents set up quicker or faster or larger or longer or more efficiently so that the heat can go from the camera itself to the outside of the camera bottle? What control do we have over convection? The only thing we control about the convection in SCINI's camera bottle is what type of gas is doing the convecting. So here's what I want you guys to do. I want you to figure out what type of gas we need to put in SCINI's camera bottle to make these convective currents more efficient. What type of gas would be a good substitute for just normal air that we breathe to stick inside this camera bottle? We obviously don't want it to be flammable, right? We don't want the SCINI to catch on fire or once it goes down on the ice by a short or something occurring in the electronics of the camera bottle. So flammability is no good. And in fact, in general, we want something that's not even going to react with any of the components inside SCINI's camera bottle. So we're looking for a gas that's non-flammable, a gas that's non-reactive, and we're looking for a gas that's very cheap to produce and use. I suggest you start with the noble gases. Over here in group 18, they've got a full outer energy shell. They're stable elements. They're not going to react. They don't want to react. There's no incentive for them to react with anything or anybody. They're going to make a very good starting point for your search to figure out what type of gas we can pump into the camera bottle of SCINI to increase the effectiveness of these convective currents.